I'm going to tell you about the Mixwell brushes, and my son Ethan is going to tell you about how he made it really fast. Okay, so let's start with a marbled scarf. Here an artist drops some colored paints into a viscous bath and then uses a rake or a comb with cylindrical tines to induce strong drift and significant stretching in the flow. In the process, the colors get mixed together to produce these beautiful marbled patterns. So if you try to use physics-based fluid simulation to model this, you're going to struggle with extreme resolution, low dissipation, and high compute costs. Plus, we want to make it fully interactive so we can explore these patterns. So how can we do that with physics-based fluid simulation to see these beautiful scarves, such as these ones by Brittany Locke? It's a really wonderful marbled scarf. So here's a bouquet pattern scarf modeled using Mixwell. We model drift from cylindrical tines using reverse drift functions. Mixwell enables perfectly parallel GPU evaluation of arbitrary-resolution 2D fluid simulations for progressive simulation and rendering. And we can also exploit periods to evaluate even faster. So the key thing is we have a special case solution for cylinder flow, shown here. Cylinder flow has been known for centuries. The equations for the stream function are here. The velocity field is just a simple rational form like this. So given this velocity field, you can time step particles or reverse time step texture coordinates to get the drift. But James Clerk Maxwell knew that the drift around a cylindrical tine could be computed analytically. He actually came up with a solution for the analytical solution of a time on a streamline. So if you knew what time you're at, you could jump to another time. In angle streamline coordinates, you can write down the particle drift as a function of time, but it's an implicit nonlinear system involving incomplete elliptic functions. So what? We've got shader toy. Let's evaluate it. Here's a Newton solver. We can evaluate in shader toy and compute the drift of the texture coordinates at any time for any pixel in real time. So if you know this curve of how the particle gets pulled up and around and behind the thing, and you know your time, you can jump forward or backwards in time to evaluate wherever your drift is. The most important special case is 1D drift, a long stroke. This causes these classic streaking patterns in marblings. You have this logarithmic singularity and fast decay. This 1D drift function can be written down exactly as elliptic functions shown here. And we have a fast series approximation that's 70 times faster and does nanometer accuracy, which is good enough for me. For arbitrary strokes, we have the Mixwell brush. This allows you to see the effect of a cylindrical brush being pulled through the paint without the cylinder. We don't leave our paintbrushes in the paint. How do we do that? We incompressibly insert a cylinder, advect a little bit, and then pull it back out. Mathematically, in the limit, this becomes the incompressible pullback of the 2D cylinder flow velocity field into R2. Oh my God, here it is. But visually, what is it? It looks like this. It's basically a ghost brush that shows the streamlines flowing around a cylinder that's not there. This is great because we don't have cylinders and we can time step through R2 without having to worry about all kinds of other excluded domains. So if we have a brush at X and we move it a little bit, delta X, we can compute the drift forward or backwards in time using a matrix vector multiply with a matrix K. What is this matrix K? Ta-da! It's the Mixwell brush matrix written in Kelvinlet form right here. And it's incompressible, it's sharp, it has a cusp, it's fast decay, and importantly, it's defined everywhere, so we can time step through it really fast, adaptively, as we'll see next. You can also take derivatives of this thing. People like derivatives. So you can compute the affine Mixwell brush to get pinch and twist brushes like we did with Kelvinlets. And so basically this is complicated. So we encode everything with RDFs, which means if you have a brush moving along a curve, there's a drift initial value problem that you time step to figure out the drift of your particle at some position P, naught. And then the difference between the end and the beginning position is the RDF. So we already have an RDF for 1D drift of an infinite line. This is really fast using our series approximation. We evaluate it millions of times. We love it. And it's used for all the base patterns like gel-jit and nonpareil, which are fundamental marbling patterns. So this gets evaluated very quickly. The other fundamental building block, which is more complicated, is a line segment. For the reverse drift for a line segment, for a brush moving from A to B, involves a more complicated solve. We have two solvers. The Newton solver is the most direct approach, but it's more expensive and it has artifacts due to physical singularities in the time coordinate. We have the brush solver, which we evaluate using adaptive midpoint. Think of it like ray marching for flows. And this basically gives us a floating point accuracy in a shader if we need it. But with less accuracy, it's smoking fast. We can do arbitrary line segment patterns like tri-waves. You can also integrate other curves, such as these circles, or sine wave combs, or whatever you want. And this runs in real time. To use these RDFs, then we can easily describe general marbling patterns, such as these classic ones. And next, Ethan is going to tell you about how to make it run in real time, make it fast.
Hey, so one of the biggest problems that you're going to run into if you try to simulate complex marbling patterns is the enormous amount of high-frequency detail that these transformations can produce. We can't filter these transformations, but we can supersample them. So we employ a progressive sampling approach to achieve a clean image over time. We initialize each sample position with a random point in each pixel, and then we apply all of the RDFs in reverse order to get the original position that that point came from. And we can repeat this process as many times as we need to achieve a supersampled image. Despite that, the one sample per pixel already provides a pretty accurate preview of what the overall shape of a pattern is going to look like. You can see here in our interactive editor, you can actually scrub the patterns and see all of the results of the mixing pretty much immediately. Again, since none of this is resolution dependent, you can also zoom in as far as you want. You can actually zoom all the way down to floating point precision, and everything will stay totally sharp. We can actually relinquish this capability to evaluate certain patterns a lot faster than we would otherwise be able to, which is what I'll talk about next. So we can exploit periodicity for certain periodic patterns, even if the overall pattern isn't periodic. You can see this birdwing pattern. It's made up of 4 periodic RDFs, but they're periodic in different ways, and the overall composition of all of them is actually not periodic at all. You can see this image is slightly different everywhere. But we can still take advantage of the partial periodicity to evaluate this particular RDF a significant amount faster. So if we look at the first tri-wave, remember everything is evaluated in reverse order. Once this advects the texture coordinates, we can actually rearrange this expression to just get the drift from the tri-wave. And this is a periodic function, so we don't necessarily have to evaluate it on the entire image. We can cache the intermediate drift maps and expand them as needed just by wrapping them. So if we reformulate our RDF composition to work in terms of drift and then reconstruct position at each step, not every single one of these RDF evaluations has to run for the whole image. So we can see here the first tri-wave only has a very small period. If you have 2 RDFs with the same period, they combine trivially, but if you need to combine more than if you need to combine RDFs with different periods, you can use the least common multiple function to find the smallest multiple of their periods for which they are properly aligned. So if we have 2 periodic functions, A and B here, with their respective periods, and we have C, which is a composition of A and B, in this case they're just adding them together, then the period of C is the least common multiple of the periods of A and B. And this naturally extends to 2 dimensions component-wise. Here it is for 2 other inputs with periods 3 and 5. The common period is 15. So we can do this iteratively at each step of the RDF evaluation process to only evaluate each RDF on the smallest period on which it is, on the smallest domain in which it is periodic with all of the RDFs before it. So looking back at the original birdwing pattern, we start with our first tri-wave. We add the second tri-wave after, which has the same period, so the overall period doesn't change at all. Then we add a noisy, non-parial vertical comb, which never repeats on the x-axis because of noise, but it's one-dimensional, so repeating on the y-axis is trivial. And then we add a horizontal gel jet comb, which for the image of this size doesn't actually repeat. If it was a little bit bigger, it would repeat on the y-axis, but in this case it doesn't. But since most of the cost was in the 2 expensive tri-wave passes at the beginning that got the biggest reduction, we actually save a majority of the time here, and we can evaluate this particular pattern very fast, 21 times faster in this case. Instead, if you want to fully embrace the totally arbitrary evaluation of this method, you can actually plug it almost directly into a path tracer. The sampling of path tracers is almost exactly the same as the sampling that we use. And with the progressive sampling, you can see the changes that you make to the comb patterns in almost immediately. You can see here disabling all of the different passes, enabling them, changing their parameters. You can see the results immediately. And since this is being simulated directly in the material, there's no intermediate baking to textures, which also means that everything is totally resolution independent. So you can zoom as far in as you want, and everything will stay sharp. This is a 16K render. You can see it on our poster outside. If you want to see more, you can check out our paper. And we also have demos on our webpage. You can check out our demo, you can check out some different shaders related to this, and you can check out our code. Thanks for coming.